In the last video, I presented you the idea of what an oxidation number was, the idea that different substances within a molecule, so different atoms, will actually be pulling on electrons different amounts, and that leads to some of them gaining or losing electrons, and that's all based on the electronegativity of different atoms. This helps us keep track of where electrons are, what they're being given to, what they're being taken from inside of different molecules. That's helpful in a redox reaction because a redox reaction is the transfer of electrons. And so we can actually keep track of where all the electrons are and where they go by using an oxidation number system. Now, instead of drawing each individual Lewis structure, we actually have a set of rules that help us understand how to keep track of oxidation numbers. And those are the rules that I wanted to go through with you today. So first rule is the oxidation number of any pure element has to be equal to 0. So let's take a look at a few examples. So we have sodium, hydrogen, oxygen, and then P4, which is one of the ways that you find phosphorus in nature, is just as 4 atoms stuck together. So sodium is a pure element. We know it's a pure element because there's no charge written in the top corner and it's not bonded to anything. It's just written all by itself. That means it has an oxidation number of 0. This rule that oxidation numbers of pure elements have to be 0 also applies to diatomic substances. Substances like H2, substances like O2, they have oxidation numbers of 0. Keep in mind your diatomic substances would be things like H2, hydrogen, N2, nitrogen, O2, oxygen, or any of the halogens, F2, Cl2, Br2, or I2. They are all called the halogens, and those are all of the diatomic substances. I like to remember them as the gens. They are hydrogen, nitrogen, oxygen, and the halogens. Everything that ends with gen on the periodic table is actually diatomic. This substance over here, P4, also has to have an oxidation number of 0 because it's just an element. It's just phosphorus, even though there's lots of them. It has no charge, so it has to have an oxidation number of 0. It's probably important to understand why at this point. Keep in mind, if you had something like hydrogen, that's 2 hydrogens bonded to each other. If it was phosphorus, that's 4 phosphoruses bonded to each other. This is all based on the electronegativity. So each hydrogen has the same electronegativity. So when they pull on electrons, they pull the exact same amount. Imagine having a tug of war with yourself. You would both be pulling at the exact same strength, which means nobody would move anywhere. And these 2 hydrogens are pulling on these electrons with the exact same strength, which means neither gains or loses any electrons, and that's why our oxidation number is 0. So that is our first rule of oxidation numbers, that the oxidation number of any pure element must be 0. Rule number 2, on the other hand, is that the oxidation number of any ion is the charge of that ion. So let's take a look at a few examples here. So we have calcium 2+, NaCl, and Mg3N2. So in any ionic substance, the charge is the oxidation number. So for calcium 2+, the oxidation number is just 2+. And this should make sense. Remember, charges are there to help you keep track of how many electrons were either lost or gained. Positive 2 means that it lost 2 electrons. Oxidation numbers are just keeping track of where electrons are and whether they've been lost or gained. So really, it's just an oxidation number of positive 2 because we know from the charge that it lost 2 electrons. So let's take a look at something like NaCl. This may not seem like an ion because there's no charge written right away, but we know that this is actually made up of sodium ions and chlorine ions. And how do I know that? Well, I know that because it's an ionic compound. It's made of a metal and a non-metal. And so each of those substances has a charge, and that's what's holding this compound together. And since the oxidation number is just the charge, it means that the oxidation number of sodium is +1, and the oxidation number of chlorine is -1. If we take a look at this substance, Mg3N2, you can all of a sudden recognize it's the same. It's a metal, magnesium, bonded to a nonmetal, nitrogen. So we can just use the charge of each of these substances to find the oxidation number. You can use your periodic table to look for charges, or you can backtrack based on the actual structure of that ionic compound. But the charge of magnesium is +2. The charge of nitrogen is -3. So those are the oxidation numbers for magnesium and nitrogen. So that's rule number 2. The oxidation number of any ion is the charge of that ion. So let's move on and take a look at rule number 3. So rule number 3 has to do with fluorine. And fluorine in a compound always gets an oxidation number of -1. Now, fluorine is the most electronegative element that exists, which means it will always take electrons from other atoms. So let's work through just a few examples to find some oxidation numbers. So if we were to take a look at this, we know that fluorine must be a -1. As the most electronegative element that exists, it will actually pull electrons away from whatever it bonds to, as long as it's a different substance. And so it will gain that electron, that negative charge, that like negative oxidation number, and that means that hydrogen's actually going to lose an electron, making it have an oxidation number of +1. If we were to take a look here, fluorine has an oxidation number of -1. Now I need to point out here that even though there are 2, we actually want to know the oxidation number of an individual atom. And so that means that the fluorine is actually going to have an oxidation number of -1. There are 2 of them, so that means each is actually going to gain 1 electron. Well, that would tell us that the oxygen has to essentially lose 2 electrons, only because it's bonded to fluorine. Let's take a look at our very last one, F2. F2 has to have an oxidation number of 0. And why is that? Well, this is a pure element. Keep in mind the difference between a compound, 2 different elements bonded together, and an element such as F2, where it's just a single one of those substances. Okay, so that's rule number 3. If you have fluorine in a compound, it always has to have an oxidation number of -1. Rule number 4 is all based around hydrogen. Hydrogen has a pretty low electronegativity, and so that means that it is going to give up 1 electron. So if hydrogen is in a compound, it gets an oxidation number of +1. So these are our examples. So we have HCl, we have H2S. HCl, the H is going to give up its electron. We know that because H gets an oxidation number of +1. That means if it's giving up its electron, it has to give it up to the chlorine. And so the chlorine is going to get an oxidation number of -1. Now, in our other example here, we have 2 hydrogens, but each of them has an oxidation number of +1. Since each of them has an oxidation number of +1, they're each giving their electron to sulfur, meaning that sulfur is essentially going to gain 2 electrons and get an oxidation number of -2. So that is our next rule. Rule number 4, if hydrogen is in a compound, it gets an oxidation number of +1. Rule number 5, if oxygen is in a compound, it usually gets an oxidation number of -2. So to work through this, I wanted to show you some examples so we could figure this out. So what I would do very first, I think you could solve this one in 2 ways. Number 1, you could recognize, well, oxygen has to have a charge of, or an oxidation number, sorry, of -2. And if it gained 2 electrons, well, it had to gain them from magnesium, and so it gets a charge or an oxidation number of positive 2. The other way you could recognize this is you could recognize this as an ionic compound, a metal and a nonmetal. And so the charges are going to be the oxidation numbers. And you could actually do the same right here. You have a metal and a nonmetal. So it's made up of O2, so O minus, and Na plus combined together in an ionic compound. So that means oxygen has to have an oxidation number of -2, and sodium has to have an oxidation number of +1. But in something like water, H2O, you see, oxygen we know is going to have an oxidation number of -2 because it usually gets that oxidation number. And we also know that hydrogen gets an oxidation number of +1. And this should make sense based on its structure. The hydrogens have less electronegativity than the oxygen, so they're going to give up their electron to that oxygen. Each of them gain just a slight positive. That gives the oxidation number of +1. The oxygen gains those 2 electrons from each of the hydrogens, giving it the oxidation number of -2. That's going to lead us to our next example, H2O2, which is called hydrogen peroxide. And I wanted to show you an example that is different. You see, hydrogen peroxide is not like water. It has a hydrogen bonded to an oxygen, bonded to an oxygen, which is bonded to a hydrogen. What's happening in this structure is this oxygen is gaining an electron from the hydrogen. So the hydrogen is going to get its positive. This hydrogen over here, same thing, gets a positive by giving up its electron to this oxygen. But here, there is equal pulling in both directions because oxygen is bonded to oxygen. That is literally what a peroxide is 2 oxygens bonded together. Anytime you have a peroxide, oxygen is actually not a -2, it is a -1. It is one of the exceptions to the times that oxygen is a -2. Hydrogen does not have that exception. It's still going to be a +1 because it's giving up its 1 electron. But that's just something to be careful of. If you get to more advanced redox reactions, you may see things that are called peroxides. Usually you can identify them as having 2 O's actually bonded to each other. And that means oxygen only has a -1. But in high school chemistry, it's a pretty good bet that this is all you need to know, is that oxygen has an oxidation number of -2. Rule number 6, the sum of oxidation numbers in a compound must add up to be 0. So let's take a look at a few examples. So I have Mg3N2 to start, and we can actually do this one based on what we knew before. We knew that there is magnesium with a +2 because it's an ionic compound. Nitrogen has an oxidation number of -3. Now you may be wondering, like, well, how does that add up to be 0? Well, if we take a look at the oxidation number of magnesium is +2 because that's the charge of magnesium. The oxidation number of nitrogen, well, it's -3 because that's the charge. But we need to look at the number of atoms. And there is 3 magnesium atoms. There are 2 nitrogen atoms. And if we look at the total of each oxidation number, 3 atoms, each with an oxidation number of +2. Well, it's a total oxidation number of +6 for each positive thing. Same for the nitrogen. It's going to be -6. There are 2 atoms, each with an oxidation number of -3, gives them an oxidation number of -6. Add those all up together, you get an oxidation number of 0. So we can do the same to figure out other substances. We can take a look at the oxidation number. So the oxidation number, we can look at the number of atoms, and we can look at a total, and we can figure out what's going on. So there are 2 manganese atoms and 7 oxygen atoms. And we don't necessarily know manganese because it can take all kinds of oxidation numbers. But we do know oxygen is going to have a -2. And so that's going to give us a total of -14. So there are 14 negative oxidation numbers. And it has to add up to be 0 because that's the rule. The sum of oxidation numbers in a compound must be 0. So that means there has to be 14 positives in total. And that's divided amongst the 2 manganese atoms, meaning that each manganese has an oxidation number of +7. Now, if you were to try and find out the oxidation numbers in a compound, this is what we actually care about. We care about the individual oxidation numbers. We don't actually care about the totals. It's just a way to help us get to those individual oxidation numbers. The other thing you may want to try is actually not even using this chart. This chart is helpful when you first start, but finding oxidation numbers is kind of the first step in working with redox reactions. What you want to get to is thinking kind of like this. I have an oxygen, has an oxidation number of -2. There are 3 of them. That's a total of -6. That means there has to be 6 positives. 6 positives divided amongst 2 chlorines is +3. This is the point that you want to get to, but if you're not there yet, use the chart to help you find those oxidation numbers. So that's rule number 6. The sum of oxidation numbers in a compound is 0. We have one rule left, rule number 7. So rule number 7 is the sum of oxidation numbers in a polyatomic ion is the charge. So let's take a look at a few polyatomic ions. Remember, you can identify a polyatomic ion because it's more than one element combined together, and it has an overall charge in that compound. So if we wanted to find the oxidation numbers, let's set this up the way we set up our other substances. So we want to know the oxidation number. We need to look at the number of atoms. And then we need to look at our totals. So we know that there's 1 nitrogen, 3 oxygens, and we don't know the oxidation number of nitrogen. There's no rule for that, but we know the oxygen has to have a -2. There is a rule for that one. That gives us a total of 6 negatives. So now if we start thinking about what does this have to add up to be, we have to use the charge this time. It has to add up to be -1, which means the total of positives have to be +5, which means the nitrogen has an oxidation number of +5. So the oxidation numbers in this compound is that oxygen has a -2, nitrogen is a +5. Let's try that again with dichromate. So Cr2O7. So we need to take a look at our oxidation numbers, our number of atoms, and our total. So we have 2 chromiums. We have 7 oxygens. There's no rule for chromium, but there's a rule for oxygen. So there's -2, which gives us a total of -14. Because it's a polyatomic ion, it has to add up to be the charge. It has to add up to be -2, which means there are a total of 12 positives. That's divided amongst the 2 chromium atoms. So each chromium has an oxidation number of +6. Those are your oxidation numbers in this compound. We have one last example left, and I want to try and do this one without the chart so that we can take a look at how we would do this. Oxygen, we know, has an oxidation number of -2, and there are 4 of them. It gives us a total minus 8, but it has to add up to be minus 2. What does that mean for sulfur? Positive 6. Positive 6 and negative 8 is negative 2. We got that negative 8 because of the 4 oxygen atoms. These are our rules to calculate oxidation numbers. They're all based off of using electronegativity, but rather than having to draw each individual atom, it really is just about learning those rules. And the biggest thing you can do is make sure you practice these rules so that when you come across them, you know how to deal with different substances in different situations. So thanks for watching, and I'll see you next time.